Hello and welcome to the fourth lesson in our fifth unit, sine functions, for our grade 11 University College math class. So today we're going to be looking at the last two transformations of the sine function. So I'd like to draw your attention to this form of the sine function right here, y equals a times sine bracket x minus d close bracket plus c. So in our last lesson we focused on a. And A tells us a couple of things. It tells us first whether or not there's going to be a vertical reflection across the equilibrium axis. If our A value is negative, there will be a reflection. If our A value is positive, there will not. The A value also tells us what would be the equivalent in a quadratic function of whether it's being expanded or compressed. So it also tells us the stretch. When we're talking about sine functions in particular, it refers specifically also to the amplitude, the distance from the equilibrium axis to the highest point or the equilibrium axis to the lowest point. So we're going to look at the last two transformations today, which are D and C. And these correspond respectively to horizontal translations and vertical translations. Now horizontal translations, let's have a look at this first sort of little table thing here. A horizontal translation, when we're talking about a periodic function, we call it a phase shift. So a little bit of new terminology there. And I also want to point out that our bracket comes with a negative in it, which means that our d value is going to be the opposite of how it appears. In the same way that in a quadratic, in a parabola, x minus 2 is actually x minus positive 2. And x plus 3 is x minus minus 3. Now if that's confusing to you because you don't really remember quadratics, then don't worry about it. We'll talk about it again when we get to the sort of sample sketches here. The last value, vertical translations, are the constant value at the end, and we take those at face value. So plus c means that our whole sine function is going to be shifted up c, and if it's minus, it would be shifted down c, which interestingly enough, and I want to point this piece out right here, I'm going to erase it only to highlight it again, the y value, the equilibrium axis is the c value. So if our function is like plus 6, then our equilibrium axis would be y equals 6. If it was minus 3, then our equilibrium axis would be y equals minus 3. So that's how it plays out. We're going to do some sketching. This is probably the most complicated lesson maybe of the whole course. There's a lot of stuff to keep up in the air here. So we're just going to do our best, and I'm going to show you all 4 examples really thoroughly. So this lesson will be a bit longer, but hopefully it will be, that we're being so thorough will help you get it better. Always takes a little bit of time for sure. All right, let's jump in. Y equals sine x plus 1. So the first thing we want to tackle is some of the important information. So our amplitude is going to be our A value out front. Now it's invisible, but our A value would be equal to 1 here, which means our amplitude is equal to 1. P is the period. How long does it take for our function to start repeating? As I said, we're not doing any horizontal expansions or compressions, so it's going to be 360 degrees pretty much all the time for our course in the grade 11 University College math course. Now PS is some new terminology that stands for phase shift. Now a phase shift would show up if you had a sine and then an x plus or minus something here. Now we don't have that, so that means that there is no phase shift. So phase shift in this case is none. The last one is going to be vertical translation. So our vertical translation, as you recall, is the constant number showing up here at the end. So we do have a vertical translation, and we are going to write that out as 1 unit. And we need to provide a direction here. So vertical translations go up and down, so that's a plus 1. So that means we are going to go up 1 unit. Okay, we're going to hold off on the range until we're done graphing this thing or sketching it. So once we have this information down, I like to see sort of what our horizontal scale is going to be. We're going from 0 to 360. So what I usually do at this point is I usually sketch in my y-axis. So I'm going to do that right here. There's y. Put a little arrow. Put a little arrow on there. Call it y, and I'm going to label my 0 point here. There's my 0, and I guess it would also continue down forever in that direction as well. So I have this whole horizontal line to get to my 360, so I'm going to use all the space I have, and I'm going to put 360 here at the end. As before, when we were sketching in the last lesson, I'm going to do halfway is 180, halfway between those first two is 90, and halfway between those last two is going to be 270. So I'm going to start just by breaking this up into the places where my 5 points are going to go. There we go. So I have this labeled in terms of all of my horizontal places. Now I need to put a vertical scale on my graph. And the way that I want to do that is first to look at my vertical translation and combine it with my amplitude, since that's going to give me my height. I'll show you what I mean by that. So you don't have to write this part down. I'm just going to sort of sketch it out here. So I also know that my amplitude, as I said here, was going to be 1. So if you can imagine, again, you don't have to write this down. Imagine what we've got here is our vertical translation, which takes our whole equilibrium axis, which was previously on the x-axis. Now it's going to be up 1 unit. So there it is. That's going to be y equals 1. Now how high above that am I going to go? Well, I'm going to go 1 amplitude above that to get to my highest point. So my highest point, if this was 1, will be 2, and my lowest point will be 1 unit below that, which will be 0. So all I need to make sure I have on my vertical scale on my y-axis, I need to make sure I get all the way up to 2. That's the thinking. So again, just to recap that, I'm looking at what my equilibrium axis is going to be, which is my c value, and then I add my amplitude to it to find my highest point and subtract my amplitude from it to find my lowest point. So again, hopefully that works. Again, I'm just going to erase that because that's just sort of me needing to draw on something so you can get it. Now let's actually put that high point of 2 on our scale here. So 2 is the highest. So I'm using all the space I have, and then there's 1, and then with 0 is already on there. All right. So now that I have the vertical scale and the horizontal scale, I'm going to start by putting on my equilibrium axis. Now that's going to go through 1. So I'm going to dot that through 1, parallel to the x-axis as well, as close as I can. Again, it's just a sketch. Trying to keep it decent. And there we go. And I'm going to label that y equals 1. So there's my equilibrium axis sketched in, but pretty much parallel to the x-axis. Now I'm going to put on the 3 points that sit on the equilibrium axis for every sine function, which is the beginning, there we go, the middle, 180, and the end, 360. So again, 3 points always on my equilibrium axis. Now I'm going to put in my high point and my low point depending on whether or not there's a reflection. So if I look at this, I see that my a value is positive 1. So this won't be a reflection. My function is going to go up before it goes down. So that means my high point is going to occur at 90. There we go. And my low point, 0, is going to occur at 270. All right. So there are our 5 points. Now I'm going to sketch this together, trying to make it, again, as curvy as possible, because it is a curve after all, not a collection of straight lines. Let's get some arrows on the end of this bad boy. There we go. And now, as before, I'm going to label all 5 points. So at 0 degrees, I'm at a height of 1. At 90 degrees, I'm at a height of 2. At 180 degrees, I am at a height of 1. At 270 degrees, I'm at a height of 0. And at 300 and, I'm trying to find where to go. We'll go here. 360 degrees, I have a height of 1. So I've labeled all 5 points. Last thing I want to do is include the function itself, which is y equals sine x plus 1. All right, there we go. So that is a fully worked through and labeled sketch of y equals sine x plus 1. Last thing I want to do here is consider the range. So the range, interestingly enough, is something that I know by looking again at what is my c value. So my c value was 1, and I add the amplitude to that to find that my highest point is 2, and my lowest point is, well, I didn't really label it. My lowest point here is going to be 0. That's the height of 0 right there. So I'm going to articulate those high and low points in my range. So the range starts the set of all y, such that y is an element of real numbers. Real numbers because we have a continuous line. So I put my low point, my y, my high point, close the brackets. So I know that y will be less than or equal to 2, since it will hit 2, and then there will be values less than that. But 0 will also be less than or equal to y. And that is our range and the sketch of our first example. So I'm going to stop this here, and I'm going to work the next example next. You can rewatch this just to sort of hear what I'm saying. I'm going to try to be just as thorough when I go through the second, third, and fourth examples as well. So this is part 1. We'll see you in part 2.